This is Kosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. We are joined, as usual, by Brad. How you doing tonight, Brad?
Hey, guys. I'm good. I'm here.
All right. Mike?
Howdy, guys.
Doing good over there?
Absolutely. Wearing my nice purple shirt.
Nice shirt.
Looks great.
Yeah, it does. And I am Russ. This is Kyle.
How's it going?
And Randall. How are you
Yes,
doing,
that's
sir?
me.
That is you.
Mm-hmm.
The storm is lingering.
It is.
It is. I could have changed it, but it's so spectacular
It is.
that I thought I'd keep it up one more episode.
And
Because we
can I
will,
get-
at some point be talking about what's behind me here.
Oh, yeah.
Oh, yeah, because it's an important part of the story.
And I get to be the little peon in the corner.
That's right. Right. Somewhere Brad's in there. Yeah, I don't know why, but Brad keeps showing up in a lot of my photographs.
Yeah, it's strange. I've noticed that
I know.
trend.
Yeah, you've noticed that too.
There was a
Well,
plan.
The whole idea of what happened to the Clovis people? Where did they go? Why do we not find burials? That's to me a very interesting question. And so anything that might shed light on that, I think is valuable. Because here was the culture that occupied North America right up to the very end of the Pleistocene. And that's kind of where we could pick up with Kennett's work that we started into last week, which was wildfire and abrupt ecosystem disruption on California's Northern Channel Islands at the Alarode Younger Dryas Boundary. And of course, to refresh everyone's memory, there was the Bolling, there was the Alarode, or Alarode. I've heard it pronounced both ways, so I don't know which is the correct way. But this was that period of late glacial warming that caused the initial shrinking back of the ice sheets. The Bolling and the Alarode were punctuated by the older Dryas, which was that cold snap, which we'll probably be pulling up the Greenland ice sheet graph again, and you'll see very clearly that the older Dryas is there, but it's only a century. And it punctuates this warming trend that began around 14,700 to 15,000 years ago. That is the Bolling, older Dryas than the Alarode. Then the Alarode shifts into the Younger Dryas, and the date has been shifted forward a little bit closer to 12,800 than 12,900. Okay. So if we go back, this paper that I'm going to be referencing now goes back to 2008. So it's using a little bit older date, like a century or so older. But I think what they've done is they've calibrated it based upon using as their chronostratigraphic marker the platinum deposition in the ice, which actually has a total duration of, I think it's 21 years. So in other words, there was an initial pulse platinum, but the platinum enhancement then lasted for 2 decades, and then it tapered off. But to me, that's very interesting because it almost seems like the atmosphere was then getting recharged with platinum. Because I mean, how long would it take for the initial pulse of platinum, let's say in the case of an impact event, for the initial pulse of platinum in the atmosphere to clear off? But the fact that it extended for a full 2 decades seems to suggest that maybe there was a replenishment of the supply of platinum in the atmosphere. And if that's the case, how do you explain that? I don't know. It's all part of the mystery of what exactly happened at the Younger Dryas Boundary, which clearly seems to involve some kind of an ET event. But exactly what and where, we're figuring that out. That's what we're trying to do.
It's like an extended bombardment. I mean, is that because that
could it be? Yeah, I mean, perhaps. Although again, like I said, it kind of fades out at the end. But yeah, maybe an extended bombardment, or maybe, a bombardment that, an episode, and then a few years later, another episode.
Right.
That's really going to complicate matters, though, of course. But hey, we're dealing with nature and natural phenomena here. So we, probably have to expect that it's going to get a bit complicated. And so this is why a lot of the critics have invoked this really overly simplistic model. Well, you've got, requires an object that's going to be 1.5 kilometers in diameter coming in, and there's no way that one object like that could produce these effects on the geographic scale that we're seeing. But of course, that was never the model that was actually put forward as definitive by the proponents of the ET hypothesis. It was simply a way of getting started to thinking about it. And yeah, the critics were right. That model doesn't really make sense. So then, of course, the proponents come back with a much more nuanced model, which is actually a multiple bombardment. So then the question is a multiple bombardment episode realistic? And I think the answer at this point clearly is yes, it is definitely a possibility. Particularly, and we, in some of our recent episodes, we were looking at evidence of comets fragmenting, and this would be essentially the explanation behind a multi-episode bombardment, is that Earth encounters the stream of debris from a disintegrating comet early in its stages in its hierarchical stages of disintegration, before it has the chance to devolve into mere dust or small meteorites the size of your fingernail, because we're talking about maybe Tunguska type objects or larger. So in this paper in 2008, and I'm jumping back to 2008. We did talk about the Channel Islands earlier. We didn't get into full depth though about the evidence for wildfire there, and so I wanted to kind of address that, readdress that, because it kind of leads into the later papers from last year or the year before, basically looking at on a much larger geographic range of biomass burning. So anyways, in the paper that was authored by Douglas Cannett and others, and his son JP, also I think we talked about Alan West was on there, Thomas Stafford, that you guys have had some contact with regarding, is it Hall's Cave?
Hall's Cave.
Hall's Cave, yeah. So hopefully we're going to do a podcast from Hall's Cave in the near future. You guys are working on setting that up?
I am. It's in the planning stages.
Okay, great. So in the paper, they say that the rapid extinction of many Rancho La Brean animals, we've defined that term a couple of times, okay, is closely timed to the Clovis cultural assemblage that abruptly appeared and disappeared across North America between 13.1 and 12.9 Ka. And we all know that Ka means thousands per annum or 1,000 years, right? And immediately preceded the Younger Dryas cooling. They go on to say that our opinion is that Martin's longstanding hypothesis, and Martin is referring to Paul Martin, who was the primary proponent of the idea, the overkill idea, that human hunters were responsible for decimating the great megafauna. And presumably the way his model is set up is that they hunted the mammoths down to extinction. Once the mammoths were gone, they were key herbivores in maintaining the stability of the system. So once they were gone, it had repercussions all the way down through the hierarchy that led to, presumably, and I've never really seen, the proponents of this idea addressing, well, why did camelops go extinct? Why did the Ursa spalaeus go extinct? Why did these other animals go extinct? They weren't hunted. They weren't hunted to extinction, were they? You can't Yeah.
How do the mammoths hold the whole thing? Is that what you were saying?
Yes. Yes.
Yeah, that's.
Hmm.
I don't
Yeah.
understand that either. You're right. Yeah.
Right. So, anyways, they're saying that our opinion is that Martin's longstanding hypothesis that human hunting was responsible for this extinction, called the overkill event, is not supported by the available data. And I would obviously have to agree with that. And, that was my perspective on it 30 years ago, maybe longer than that. When I looked at it, I says, this just doesn't make sense. And even prior to the extraction of the Greenland ice cores and the first publications in 1993 that showed these massive climate spasms that we have been looking at, when we see these huge spikes going back and forth. Even before that, the evidence that there was some kind of catastrophic event or series of events around that time span was already pretty robust, right? And the fact that there was already known to be serious changes, geological and climatological changes and so on, that were associated with the same time frame that the megafauna disappeared, always seemed to me to be pretty convincing evidence that, that made more sense than the idea that roving bands of hunters with spears were somehow able to, which, and I'll do an aside here, and trying to find out, this is a tricky problem. What was the population of the planet, the human population, at the end of the last ice age, right? When we come up to the Younger Dryas Boundary, during that Paleolithic period, what was the population? Well, I've seen the estimates range from 5 million to 10 million people worldwide. Is that true? I don't know. But it's, some of the best guesses by those who have looked at the evidence and tried to put together some sense, some understanding, some perspective on human population. Well, I've seen estimates that the population of woolly mammoths, or mammoths, I'll say mammoths because it's got to encompass all of the species and subspecies, the Columbian mammoth and the, you got the woolly mammoth, which is basically just one of four. The imperial Mammuthus imperator, Mammut americanum, which is the mastodon. But in any case, you got these species, and they were prevalent, and then they were gone. And the numbers, that's what I'm getting at, the numbers estimated for those creatures, the proboscideans, was about 12 million that I've seen. So let's take in that range of the average of 5 to 10 million, say 7.5 million people. That means that there were less people than there actually were proboscideans roaming the planet. So just when you start contemplating that, you go, okay, how is it even possible to think that they then exterminated minimum 10 or 12 million of these great elephants? How the hell? And, in the day, and we'll get into more discussion about this, of course, because it's such a critical part of deciphering these events and solving this mystery. But the assumption is that the wave of extinction started in Western Europe, in the British Isles, which of course were not British Isles, and moved east and actually came across the Bering Land Bridge. And the assumption was that the extinctions in North and South America would have been later than the extinctions in Western Europe. However, that idea kind of became entrenched maybe as long ago as the 50s or 60s, but subsequent discoveries and datings have shown that there were proboscideans in Western Europe at 13,000 years ago. So that kind of destroys that model of extinction wave following the migration of humans, which was a central part of the overkill hypothesis. Okay, so in this article, they go on that the overkill event is not supported by the available data. The reasons are that there is a near absence of kill sites for many of these genera, including camels and sloth. The event was rapid, encompassed numerous animal taxa, and had a large geographic extent. In addition, increasing evidence for pre-Clovis human occupations negates an explosive occurrence of people rapidly expanding throughout the Americas. The rapid onset of YD cooling is recorded throughout the Northern Hemisphere in equatorial climates and provides another potential explanation for the abrupt extinction event. In the absence of alternative mechanisms, however, based on 97 geoarchaeological sequences across North America, Haynes, remember him? C. Vance Haynes, 2008. We quoted him early on because he was one of the very distinguished archaeologists that acknowledged that there was something really extraordinary that happened at the Younger Dryas Boundary and said, you guys need to look into this further. And it was that, that work of his that led to Firestone taking that first closer look at the black mat layer, because it was Vance Haynes that identified and wrote papers on this ubiquitous black mat layer that was turning up at so many of the Clovis sites. And it was C. Vance Haynes who pointed out that Clovis artifacts are found below the black mat layer, but not above it. The extinct megafauna are found below the black mat layer, but not above it. So that's who the reference in here is to Haynes. However, based on 97 geoarchaeological sequences across North America, Haynes in 2008 argues for a dramatic environmental event at 12.9 Ka. He argued that the base on a physically distinctive YD black layer at 70 of these 97 localities dates to approximately 12.9 Ka and serves as a stratigraphic marker horizon, a thin stratum where Clovis artifacts and select Rancho La Brea fauna occur below, but never above this unique bed. So they go on to say that magnetic spherules are concentrated at the base of the best dated of these distinct black layers at Murray Springs, Arizona. And we need to get down there because Murray Springs is where the black mat layer is actually very distinctly preserved, much more so than at Blackwater Draw, at least from what Brad and I saw when we were there. And these magnetic microspherules were found in association with an assemblage of numerous other exotic materials identified in many other terminal Clovis Age deposits. Many of these exotic materials are found in sediments associated with documented extraterrestrial impact events. And the two that he cites here are Cretaceous Tertiary Boundary and Tunguska, both of which are key key sites that provide insight into understanding the Younger Dryas. So obviously, both of those sites are going to be worth further discussion because the lessons gleaned from either of those two sites has such direct relevance to understanding the Younger Dryas. Although much remains to be learned about this boundary layer, the co-occurrence of these exotic materials forms the basis of the Younger Dryas boundary cosmic impact hypothesis. Large cosmic impacts can have major effects on Earth systems and are known to trigger abrupt climate shifts, widespread biomass burning, and animal extinctions. And of course, all of that was then associated with the KT boundary, right? There was evidence, and Wendy Wohlbach did a lot of that work back in the 80s, showing evidence for massive scale wildfires at the KT boundary. And of course, a lot of others have done work showing the extinction event. And then, of course, we found the impact proxies in abundance at the KT boundary. And many of these magnetic rains and the nanodiamonds, which we haven't really talked about in detail yet, but the nanodiamonds found at the KT boundary are almost identical to the nanodiamonds being found at the Younger Dryas boundary. And when I pull up and we look at the pictures and so forth, you'll be able to see for yourselves. They go on to say, so the three things: abrupt climate shifts, biomass burning, animal extinctions. The recognition of mass extinction at the KT boundary attributed to a major cosmic event, along with the presence of a significant number of similar cosmic impact markers identified at the YDB, provide an empirical basis for hypothesizing that North American animal extinctions at the end of the Pleistocene had a similar origin. These extinctions may have been caused, at least in part, by the direct effects of a cosmic impact, including both the shock wave and the heat, and subsequent major and cascading ecological changes, such as regional wildfires, climate change, vegetation disturbance, and shifts. The apparent suddenness of the event that occurred at the onset of the YD requires investigation of very high chronological resolution to test the hypothesis. Sedimentary records from the Northern Channel Islands and the Santa Barbara Basin, and I'll pull up a map in a second, that were extracted, that are studied from Ocean Drilling Project Site 893, if anybody wants to look it up. So sedimentary records from the Northern Channel Islands and the Santa Barbara Basin indicate intense regional wildfires and abrupt ecosystem disruption at the Allerod-Younger Dryas transition. The time interval coincides with a last possible occurrence of Mammuthus exilis, which was the pygmy mammoth that lived on the Channel Islands, and marks the beginning of an apparent 600 to 800 year gap in the archaeological record, both of which may be indications of ecosystem disruption on Santa Rosa. That's the name of one of the islands that they studied. Okay, here we present evidence for intense biomass burning of conifers and subsequent mass wasting of the landscape at 13 to 12.9 thousand years ago in Arlington Canyon, which is on Santa Rosa Island. This expands and complements preliminary evidence for wildfires discovered on San Miguel Island, the next island west of Santa Rosa, that date from the same time. So what they did was they looked in this Arlington Canyon, which is on the island of Santa Rosa, and they studied alluvial and colluvial. Now, alluvial, remember, deposits are the result of flowing or moving water, right? The three, you've got fluvial, which means flowing water, but alluvium or an alluvial sequence is the material that's deposited by the flowing water, right? Okay, so that the alluvial and colluvial generally means that it's going to be emplaced by gravity rather than moving water. It's the primary difference between alluvial and colluvial.
Like a landslide as opposed to a river.
Yes, yes. Okay. And then Brad may elaborate upon a secondary meaning of a colluvial deposit, but we'll save that. Okay, so
I want to throw pluvial in there while you're at it.
Throw it in, Brad. Throw pluvial.
Pluvial's from rainfall.
Yes. So you can have
the rainfall.
Baby, the rain must fall. So you've got pluvial is the rainfall. And then, of course, you've got, as a result of a lot of rainfall, you're going to have floods. So you're going to have fluvial followed by fluvial. Now the fluvial is then going to lead to alluvial, right? So that's a typical sequence: pluvial, fluvial, alluvial.
Right.
So I want everybody
enough rainfall can also lead to landslides as well. So that's
absolutely it will. Yes, that's correct. Thank you for that. Yes, you're correct. So it says that both alluvial and colluvial deposits are exposed throughout Arlington Canyon, but core sample AC003 was selected because preliminary work indicated that the basal or base deposits in the exposed sequence, in other words, at the bottom down near the canyon floor, dated to the Allerod-Younger Dryas transition and appeared similar in character to the dark sedimentary layers described by Haynes across much of North America. The section is exposed on the western side of the canyon at the base of a steep incline extending down from the Quaternary terrace above. Quaternary, what is the quaternary? Quaternary means it was basically formed within the last 2.5 million years. And a terrace is something that is actually formed by fluvial processes. Generally, the terrace is composed of alluvium. If you have a large flood moving through, carrying a lot of sediment, as the flood waters subside, it will leave behind a thick layer of alluvium. Now, if there is a permanent river established within that valley or that canyon or whatever, that may in fact be diminutive compared to the large-scale mega flood that flowed through there, what it'll do is it'll cut a new channel into that alluvial floor, which it does relatively easily because that alluvium is not consolidated yet. It's still basically soft. It has not lithified, right? So subsequent water flow that will be on the scale of more normal river flow can easily then cut a channel into that alluvial layer. Well, when it cuts that channel, what it does is it leaves two shelves, one on each side. Those are the terraces, you see. We'll be looking at many pictures of those types of terraces, okay, that flank modern river valleys all over North America. You can find these. They're generally, sometimes they can be a stepped sequence of terraces. And usually the lowest sequence is the floodplain of the modern river. But the lowest terrace was not necessarily deposited by the modern river. But when the modern river undergoes a flood episode, it may rise up and flow out of its normal channel, in which case it now spreads over the terrace, which is generally the modern floodplain. Now, when that happens, of course, the modern floods will leave layers, will deposit layers of mud and material. So if you do a core sample, you can oftentimes, you'll find that the very distinct flood layers, maybe there's every 50, 100 years, there might be a large flood rises up over the floodplain. I've got pictures that I will be showing. When we get into the geomorphology of megafloods, I will be showing pictures that I've taken at a local creek near where I live, where, back in 2009, we had this really unusual, intense period of prolonged rain, and the water rose up only one of two times that I know of in the last 30 years, because this is how long I've been living near this creek, rose up out of the channel and then spread out over the floodplain. Now, in this case, in 2009, the water rose up and it drowned the modern floodplain 2 feet thick. The water was 2 feet over the top of the floodplain, right? Now, once that water drained off, the whole, and they had, on this floodplain, which is very wise, you don't build houses or permanent buildings. You have parks, right? So there was a lot of, like 4 or 5 baseball parks. It was a park, right, on the floodplain. Well, in the aftermath of this, the whole park and all the baseball fields and everything were covered with a layer of sand, freshly deposited sand. And on that sand were current ripples. And I'm going to show you pictures of it, because this is part of the microscale evidence that allows us, by seeing smaller phenomena, to recognize much larger phenomena. But in any case, sometimes if you go through and you dig down, you can actually see that now, since 2009, there's been 11 years of additional growth, leaves falling out of the trees, forming a new layer of topsoil and stuff. So you got to go through an inch or two of stuff, but you'll still find in a lot of places that sand layer is still there. Whereas now the sand, it could have been mud. But the point is you've got these layers, but then you've got the terrace itself, which might be massive. It might be a thick layer that's 4 or 5 or 10 or 20 feet thick. And the giveaway is that you might find embedded in that alluvium boulders, right? So the alluvium itself may be very fine grained, but then embedded in there might be boulders. Rona and I, my brother, who we've had several projects where we've been building, even near where I live here. We've excavated down, let's say, to do a basement to a house, and we're looking at fine-grained clay, but then embedded in that clay might be a 4-foot boulder. And of course, that's always a pain in the ass because now you got to get that boulder out of there, right? Now we've actually dug down, and in some cases the boulders were so big that we just left them there and then cut our concrete forming for the footings just to conform to the boulder. And then the boulder was actually incorporated into, the concrete footers for the house, right? But that's my point. I'm trying to get, so all of this is digressing, but it's the point of trying to get across a picture of what they're talking about when he's talking about this terrace that's at the bottom of this canyon, okay? Because that's obviously where you're going to find a terrace, right? And he says quaternary. So he simply means from that the terrace was formed sometime within the last 2.5 million years, not necessarily from a single event, right? Maybe multiple events. So then there's an exposed 5 meter, which is about 27 feet. Let's see here. 5 meter would be exactly 16.4 feet, right? Is that what you got, Kyle? 16.4.
He's checking.
So,
yeah, sorry.
That's about right. 16 and a half feet. Okay. So the exposed 5 meter thick sequence rests upon a basal gravel that is at modern stream level and largely covered with alluvial sands and gravel. A distinctive organic carbon-rich, dark blue, blue-gray silty mud directly overlies the basal gravel. The silty mud is capped with a coarse cobble channel deposit and a second dark layer consisting of finely laminated dark gray to black sandy silt. The upper dark layer is also organic carbon rich and contains, and this is where it's interesting, carbon, which is also organic carbon rich and contains charcoal and charred tree branches up to 2 inches in diameter. Intense wildfire evidence is indicated by the presence of carbon spherules ranging 400 to 1,500 micrometers in diameter in the lowest dark layer. These spherules occur widely in the YDB layer in North America and have also been found in surface sediments associated with intense coniferous forest crown fires. Accelerator mass spectrometry carbon-14 dates for the lower black organic carbon-rich layers suggested that they accumulated rapidly at between approximately 13.0 and 12.9 Ka. Conifer forest, which consisted primarily of pine, juniper, and cypress trees, partly covered the landscape in the latest Alarode, according to the pollen and macro botanical evidence from Santa Cruz and San Miguel Islands. Biomass burning at 13 to 12.9 Ka was followed by erosion with sediments containing charcoal, wood, and detrital carbon filling the channel. This organic carbon-rich dark layer was then rapidly buried and preserved by a series of mass sediment wasting events of a denuded early Younger Dryas landscape. So you got a picture. Now you've got these forests there, conifer trees, juniper trees, cypress trees, they're growing. Intense fires burn off the forests. So now you have a denuded landscape. What happens now when it rains on a barren landscape? And it's on a hill slope. Boom, there you go. There's your colluvial. There's your landslides, right? So now you have this stuff landsliding down into the bottom of the canyon from this denuded landscape, right? So you've got evidence that there was a barren landscape that came right after this deposition of these dark layers with charred tree branches loaded with charcoal. Pretty damn suggestive. Evidence for intense wildfire and abrupt ecological disruption on the Northern Channel Islands is consistent with the vegetation and charcoal records from the Santa Barbara Basin, which is right next to the islands. I'll pull up a map here in a second. The longest and most continuous available for the Santa Barbara Channel region. Pollen assemblages, because obviously by looking at the pollen in a deposit, you can tell what kind of plants were growing in the adjacent landscape, right? Was it ferns? Was it shrubbery of some type? Was it trees? Right? By looking at the pollen, that's going to tell you what was growing there. Okay, pollen assemblages reflect vegetation changes on the adjacent coasts. So you got this basin right there next to, between the California mainland and the islands. So in that basin, they took core samples from the bottom of the basin. It was actually Santa Barbara Basin, SBB, ODB, which is Ocean Drilling Project, Site 893, right? So they pull up this core sample. They look in this core sample, and now they start looking at what kind of pollen has been preserved in that core sample. The pollen records accumulated in Santa Barbara Basin, both by aeolian or wind and by water transport. So in other words, wind is blowing pollen in, it's settling into the water, drifting to the bottom. Rivers and creeks are flowing in, and they're carrying the pollen in as well. So you have both wind deposition and water deposition carrying these pollens from the vegetation growing around the basin. The pollen spectrum is dominated by pinus, which is pine, and juniper cypress during the late glacial maximum, and these conifers persisted in the region throughout the Bowling Alarod. So in other words, you've got these pine, juniper, and cypress forests growing on the California mainland and on the island, which during, at this point, is a single island, right? It's and when I pull up the map here in a second, you'll see, right? The onset of the Younger Dryas closely correlates with a major abrupt decline in the abundance of juniper cypress pollen, suggesting that these trees were abundant regionally before, but not after 13 to 12.9 Ka. The major reduction in the mountain forest vegetation corresponded with a distinct increase in grass and herbs, mainly from the Asteraceae family. I'll show you what that is in a second, suggesting a regional shift to more open habitats dominated by grasslands, coastal sage, and chaparral communities with dispersed stands of oak. Vegetation that dominates in the region throughout the Younger Dryas and Holocene. The abrupt reduction in conifers and the shift to more open habitats regionally correlates with the most extreme pollen minima and charcoal maxima of the last 25,000 years. And this is interpreted as a wildfire indicator.
That alone could have contributed with the mastodon as they're a browser, right? They eat branches and
yes. So
exactly. If like all those trees go extinct and there's no longer any of the tree, I mean, there's your whole habitat loss right there for those guys.
There it is right there, at least in this region. So
right.
What we're doing is we're looking at a particular region right now and we're seeing dramatic change. Now the question is, does that extrapolate to other regions? And of course, this is where we jump forward by 10 or 11 years, subsequent research and so forth that shows that, yeah, it does extend to a much wider geographic range. So they say this suggests rapid ecosystem change in the wake of major regional wildfires and associated landscape disturbance. These changes are consistent with the record of wildfire from the upper Arlington Canyon section and evidence for abrupt change in island vegetation during the YD. So in other words, the evidence in the Santa Barbara Basin, which is a core sample taken from the bottom of the basin, correlates precisely with the stratigraphic analysis taken in Arlington Canyon on the island. Got it? Okay. So I will now go to a share screen, and so people can see a little bit more what we're talking about. Share. Here we go.
Probably a good time for a break. We create a little partition here.
I think that's
Are
an
you about
excellent
to wrap
idea.
this up, or can we get through this in a minute or two? Let's
No.
create a little-
Let's go ahead and take a break. I think that's an excellent idea, Brad. As usual,
is.
you've come up with a timely idea, and yes,
That's all I'm sitting here doing. When can we take a break?
Chronos.
I come through in the clutch.
The
Yeah.
god of time.
Chronos.
okay. So I'm going to stop share. We're going to have a little break, then we'll come back and we'll start looking at some imagery.
Everybody
All right.
else,
Which
will
I
be
think-
right back.
Yeah. Okay.
Great.
All right, ladies and gentlemen, thank you for waiting through our brief break. And without further ado, let's get right back into it, Randall.
Oh, okay. Well, if that's the way you're going to be, by God, let's get right back into it.
No funny business.
No funny business. Are we still sharing?
Yes,
You got
we
it.
see that.
Oh, good. Okay, we never did stop share, did we? Okay, cool. So we're going to look at the general western region. Now, as you see here, the Northern Channel Islands is this little box off the coast of California, of Southern California. We'll look at it closer. But notice all the rhombuses, the rhomboidal shapes here with dots in them. Those, as it says, are where Clovis-like fluted points have been found, right? So presumably there was a pretty thick population of Clovis people there at the, just prior to the Younger Dryas Boundary. And then the circles with dots are where black mat layers have been identified. Notice that they're in the box, they're showing a circle with a dot. So that's referencing this dark layer that we just described. That's at the base of this colluvial stuff that swept down. So, excuse me. Let's think this sequence through so we get this picture. You got forests growing there on the islands, right? You've got forests on the California mainland. Here's the islands, the present day land masses of the four islands. But then at the late glacial maximum, you see minus 115 meters. Okay, that was the island during the late glacial maximum. So what are now four separate islands was all a single landmass. Got that? So so that was 377 feet below the surface of the present ocean. The minus 115 meters. But that's what you're looking at here. And
Plus,
then you
I
can
wanted to clarify that too, that the coring there, you show the ODP, the whole 893 you're talking about, it's out in the ocean. It's the Santa Barbara Basin, right? It's
There you-
underwater.
there you
It's
go.
pouring down into the ocean. There it is. Yeah.
So there's a map, present day. Yes. So this right here is the Santa Barbara Basin. So yes, you've got a core sample from the bottom of the Santa Barbara Basin, and you have these samples taken from Santa Rosa Island. And in both cases, you're finding the pollen of these forests. So the forests are growing on the island, and they're growing on the shore over here of California. So the whole area is home to these forests that are composed primarily of these conifer trees, which are juniper, cypress, and what was the other one?
Fine.
Pine. Yeah. Pine. So then all of a sudden they're gone. So these forests had been there for hundreds of years, for centuries, right? Now they're gone. Dating right after they're gone, you now have this evidence of landslides down into the valley floor. And in those deposits at the bottom of the valley floor, you have charcoal and charred wood. So what would you, Russ Allen, conclude from this? Major wildfires, right?
Major wildfires and then enormous erosion.
And then enormous erosion. Yeah, okay. So
Right.
here's the Google Earth view where you can see the basin itself. You can actually, if you look here, you'll see the outline of the single landmass that was the island during the late glacial maximum. And it was never connected to the mainland, but it was pretty darn close. So you can kind of maybe see how it was possible that mammoths did get there, because they did. And the whole island was populated by mammoths, except Mammuthus exilis, which was the pygmy mammoth. So once they got there, and presumably maybe when sea levels started rising, what's going to happen is that the range of the mammoths is going to shrink, right? What happens to the mammoths? They get smaller. They adapt by getting smaller. They're the same species. They're not a new species, but they're like a subspecies. They've gotten smaller as an adaptation to the shrinking land area. There's the shrinking geographic range. So you've got these forests growing around here, both on the island itself and on the shoreline. And the pollen from these forests, from these trees, is being carried into the Santa Barbara Basin, both by wind and by water, and being deposited, sinking down to the basin floor. And that is where it is now being found when those core samples are being pulled up.
Do you know about how far that is? Like you were showing us how far it is from the landmass now to where the island would have been when the sea levels. Do you know approximately how far that is?
Well, yeah, we could easily figure that out.
Because there was a story, I was just remembering when you were talking about that, about mammoths getting out there, there was a story where they found an elephant like 16 kilometers out in the ocean. Now they had to help it back. It was having problems, but it is known that they swim.
Oh, a living
pretty
elephant.
Dang far. Yeah. Yes, they found an elephant like 16 kilometers offshore. So it's possible that they could have swum across at least some distance. So.
Well, let's see. I don't want to open Google Earth right now, but
yeah.
Kyle, do you have Google Earth handy?
Yeah, I can look it up.
Yeah, all you got to do, pull it up, and use the little yardstick icon, and just drag a line. And if you can pull up the same image that I've got here, you can actually see that point right there that I'm showing with the cursor that would have been the closest, proximity to the land. And of course, it would actually have been closer than that because look, sea level is low, right? So this is not the coastline.
Exactly.
Right. That's right. Yeah.
You're seeing that shelf there. So
yeah,
10 miles off the coast of Sri Lanka, they found an elephant out in the water.
And so, I'm guessing that this is probably no more than that. Once you drop sea level down by whatever I said, 377 feet, which is the minus 115 meters, that's not going to be very far for the elephant to have to swim to get to that landmass. And we know there were people there.
Right.
So if I go to the next one, these are some kind of cool graphs. If you look at the top, this gray graph here, notice the dating at the very top. This is calendar KA, so we're talking 17,000 years ago over here on the right. And then at 13,000 years, which is going to be the transition, the Allerod Younger Dryas transition. And I think at this point, they're not calibrating with the platinum deposition event because that hasn't been discovered yet. But they're showing the fire event. So notice this graph here, how you've got this prominence of the basically that tree pollen that we were discussing. I'm sorry, back up. This is not the tree. Here's the tree pollen down here coming this way. So you've got Juniperus cupressus, which is the juniper and cypress trees. And then you'll see that this line right here is the fire event, right? And so the black line here is the charcoal pollen ratio. And notice that right here, you've got this huge spike of charcoal, which marks the calendar age of the fire event. And then you'll see that right after that, the juniper and cypress pollen drops way down. And then through the course of the next 2,000 years, it basically goes way down further because you're now into that period of Younger Dryas cold, right? When you're back here, 13 to 15, this area back in here, this is the Balling Allerod warmth, right? So you see that up here, the pollen of grasses is low. The pollen of forests is high. Then you have the fire event. After that, the pollen of forests is low and the pollen of grasses is high. And if you go down here to E, notice this. This is the, let's go to the bottom. Sorry, go to F, right? And here you have the Greenland Ice Sheet Project 2 graph that we've looked at multiple times, which I never get tired of looking at. But you'll notice as we're coming here, 17,000, 16,000, 15,000 years ago, then we get to the Bolling. And notice the Bolling shoots way up and it gets really warm, like almost modern day warmth, and then plunges back down, and there's your older Dryas. Then you have the Alarod, and you'll notice that the climate is certainly not stable during any of this. Then it spikes way down, comes back up. Right here's the fire event, and then you have, the Younger Dryas cold spell, and then you have this next warming at 11.6 that finally pulls the planet out of the ice age, and then you have this graph you see climbing up to the modern day warmth, right? What's interesting to me is if you took the Younger Dryas event out of here, what you would almost have, notice and you took this Bolling spike out of here. Notice if you followed the trend line of this, notice how it comes up and it would almost form, a continuum here. You see that? Look at the trend line of the Alarod. And if you extended that up, it would become the trend line of the early Holocene. Except right in the middle, that gradual increase in warmth is interrupted by this sudden 1,300-year return to full glacial cold, which is what you see indicated by the graph back here from 15, 16, 17,000 years ago. Pretty damn interesting, I would say.
Yeah, it also looks like the Bolling period is anomalous in that.
Absolutely. See,
right,
and the Bolling, this one goes back to about 14.7. So my thought is that 14.7 would probably mark would correlate with meltwater pulse 1A, and that would mark the first gigantic episode of mega flooding
Yeah.
And then there would have been a second episode at the Younger Dryas right here with this, and then a third episode right here. And I think that is what we need to look at in terms of understanding the mega flooding, that there was probably 3 massive pulses of meltwater interspersed by smaller floods. And then coming during this early Holocene, where the graph is still climbing, we would have had a succession of really huge floods, but much smaller, larger than what is normal today, but smaller compared to the mega floods where we are measuring in spur drops. You remember what a spur drop is?
I remember the term. I don't remember exactly how much
It's like
it is.
2.6 million gallons per minute or something.
Well, it's simply a million cubic meters per second.
A million cubic meters per second. Okay.
Million cubic meters per second. And that is a lot of water.
Yeah, that's a lot of water.
A lot of water.
Also, the distance is 6.87 miles.
So there we go.
So a mammoth could have swam that.
Right.
Swim. Yes.
Swimmed.
It could have. Oh yeah.
Just try them all.
It probably could have done either one of those things. Is what you're saying. Yeah.
Yeah, and I would just like to say, as an aside here, looking at the graph and then all of this, the reactions of nature to these insane changes in the climate is just, it's marvelous. I have to say that nature is so diverse that it can deal with these changes in these different ways. It's very interesting to look back and see how the plant life changes because of the climate and sort of just continues on. No matter
absolutely.
What. It's just really amazing.
Absolutely.
Yeah.
before we go on, I want to look at the other graph, which is the graph of nitrates, also from the Greenland ice cores. And nitrates are produced during biomass burning. Okay? So in the Greenland ice cores, notice that you've got, it seems like some pretty intense events. There's a fair amount of nitrates deposited in the Greenland ice cores, corresponding back here with this phase of the, the late glacial phase. Notice how the deposition of nitrates in the Greenland ice core tracks the temperature changes as documented by the oxygen 18 isotope graph. You see this right here? Look at this. Look at how this spike and this drop coincides right here with the bottling in the Alarod. And notice how right at the fire event, 13,000, there's this huge spike of nitrates deposited into the Greenland ice, and it lasts throughout the entire Younger Dryas. So what that means is that there are repeated events that are producing these excess nitrates that are being preserved in the Greenland ice cores. NO3, that's what this is. You see over here, these are the nitrates. They are produced through biomass burning and intense crown fires. So basically, it almost appears that at least in this region, there was a whole succession of fires. Now, it would make sense that, for one thing, if you have a major climate change, right, that it'd be indicated by the drop in temperature here at the Alarod Younger Dryas Boundary. Suddenly, trees that maybe survived the fire event are not going to suddenly survive this huge temperature drop of 8 or 10 degrees, right? They die. When they die, you see what happens. Now the fuel load accumulates. And so you're going to have this succession of fires that eventually burns off everything. So then, if we look at the next slide, we'll see that this is an example of the type of tree that still grows in the San Francisco mountains now, but it's the juniper tree. And you would
have about 5 billion of those here.
Yes.
Well, not that particular species, but they are juniper trees.
Right. There's many species of this happens to be Juniperus osteosperma.
Yeah, ours are ash, I think.
Right. And then here is one of your cypress trees. This is one, as it says, one of several genera of coniferous or evergreen trees. And then you go from extensive forests of this to this. So here's going back to the graph, basically this right here, the Gramineae and the Cyperaceae compositae, that is grasses and sedges and chaparral, basically is what that is. So
overcutting, overclearing.
Yeah. So then looking on the left, you've got the Cyperaceae, a family of graminoid or grass-like monocotyledonous flowering plants known as sedges. So this is maybe not the exact species, but this would have been the kind of stuff that replaced those juniper, pine, cypress forests. So all of that, for hundreds of years, you had the forest there of the juniper and cypress and pine trees. Suddenly they're gone. You have a barren landscape, and then when vegetation comes back, it's very different, which suggests there was a major ecological shift that essentially was permanent. So there was also a lot of these, the compositae, which are commonly referred to as the aster daisy composite or sunflower family, a very large and widespread family of flowering plants. So there was a lot of these growing on the island and around in the aftermath. So picture you've got these forests, they burn away, and now the climate that prevailed when the forest was there is gone. It's a new climate that only supports the grasses and the sedges and things like this. So interesting stuff, is it not?
It is very interesting.
It is. It is. So there's maybe too many things that have to be integrated here, but, we're looking not only with the mass extinction, the disappearance of the Clovis culture, the evidence for an event or a series of events, the hypothesis that this series of events was triggered by something from out there. But what exactly? Well, I think that we ultimately have to begin looking at comets and what we know about comets. And I think that we will devote at least one or two episodes to some of the recent research on comets, because I think that what we do know from some of the rendezvous with comets is that they are heterogeneous composites of maybe diverse things. And so it's the diversity of materials composing a comet nucleus that might be able to explain the diversity of the types of fingerprints that are, left in the aftermath of an encounter with this.
Right, because the thinking is that it was there was like a primordial comet that started to fragment, and then we started getting hit by the fragments. So they're not all necessarily, they may not all be, ice balls or whatever they're going to be. Some of them are going to be rocks. Some of them are going to be nickel iron materials. Some of them are going to be carbonaceous chondrites, and then dirty slush balls. But
yeah. So in conclusion, he says that that all of this evidence we've just gone through suggests rapid ecosystemic change in the wake of major regional wildfires and associated landscape disturbance. These changes are consistent with the record of wildfire from the upper Arlington Canyon section and evidence for abrupt change in the island vegetation during the Younger Dryas. So I'll stop sharing the screen for a minute. And anybody want to take it for 30 seconds? Comments?
Well, it does seem like if that much stuff was, have they taken more cores in the ocean? That's what I would be interested in. How much material is off the coast of California and not just in that basin?
Mm-hmm.
Are there layers in there that show the burning on the land, or has that all been washed away?
Well, I'm glad you asked that question, because that's where we're going to jump ahead.
Okay.
And
I think it's curious that the fires are on the island. So is that from heat? Is that something coming from the sky? It's surrounded by water, obviously. So this is not representative in that study of what's happening in California or the rest of the continent necessarily. It's out in the middle of the water that these fires are blazing and burning everything to the ground.
Well, these islands
started out there
pretty extent. Well, I would think maybe the same. If you had a multi-impact event, and depending on the size of it, if it was, let's say 5 or 10 times the mass of the Tunguska event basically incinerated 200 square miles. And then another 500 square miles was ignited by the secondary effects of the heat. So if you have an event bigger than that, what it seems to be implying is that there must have been some type of a regional event that triggered the fire. Maybe an atmospheric burst, which could start the fires, but not necessarily leave, macro evidence in the form of a crater or even meteorites, because, Younger Dryas, all it left was microspherules. So there were microspherules found. So it would suggest that somewhere in the vicinity there was an event. How close? I don't know. I just don't know. And I have no way of knowing how you would know necessarily. But clearly what that suggests is, what we're finding is as we go through the more recent work, you're going to see that the evidence for biomass burning is pretty widespread. And could it have been set? Now, here's a possibility. An atmospheric detonation, or actually even an impact that could produce fallback breccia. Of course, then that's going to leave a crater, presumably. But
Well, and there's also the idea of, like you were saying, these enormous climate changes kill all the trees off, leave a fuel load, and then you have bad storms and a lightning strike burns the island flat. That also can.
yeah. So and it looks like from the graphs we were just looking at was that throughout the Younger Dryas there was a whole succession of fires, but the biggest fire event was right at the boundary. So
Right.
yeah, and
Seems
so
to
you've
be
got this
connected.
thing that sort of corresponds to the black mat layer that has been found at the base of the canyon. That's what was described.
So can there be a big enough blast wave that comes off of the continent and still is going that 7 miles across the water to
Oh,
then,
yeah.
light
Yeah.
up the islands too? Why not? Right.
Right, exactly. Because if you're looking at something that's, say, an order of magnitude greater than the Tunguska had a range of destruction of over 20 miles from the epicenter. You go an order of magnitude over that, and you're going to have a range of destruction. It could be up to 100 miles, right?
Sure.
And so, and who knows? I mean, there could have been an atmospheric detonation over the island, and there was probably atmospheric detonations over the oceans, but they wouldn't necessarily, obviously over the ocean, they're not going to start any fires. And the evidence is going to be completely lost because whatever secondary proxies are produced by an atmospheric detonation obviously are going to, for the most part, go into the ocean unless, they end up in the stratosphere and they get circulated around, which is going to most likely happen as well.
Is there any evidence of volcanism in the black mat? Like, would they be able to forensically tell the difference between ash created by
Yes, absolutely.
volcanic?
And the answer is no, but there is evidence of major volcanic eruptions bracketing the Younger Dryas on both sides within a couple of 100 years, which is interesting. And I have some research on that question, and I think I could pull it up, but I don't think we'll have time tonight because I want to get on to Wendy S. Wolbach's paper. She was lead author, but you had a lot of people contributing to it. It was a 2-part paper that was published in 2018 entitled Extraordinary Biomass-burning Episode and Impact Winter Triggered by the Younger Dryas Cosmic Event approximately 12,800 years ago. So you can see how the dating has been a little bit adjusted. I think this is primarily because they're using the platinum deposition layer as the datum. Anyways, this was published in, this is part 1, Ice Cores and Glaciers. Published in the Journal of Geology, 2018. They begin the paper by saying that Firestone et al. Initially posited that exotic materials found in the Younger Dryas boundary layer provide evidence of a major cosmic impact event caused by Earth's collision with a cometary swarm. See, I like that. They're gravitating towards that idea, which is really quite a bit different than the idea of just a single mass impactor, a single isolated one event, one on, boom, right? Which is basically the models that the critics were attacking, not the idea of a cometary swarm. Very distinct processes, right? I think if we're looking at a cometary swarm, yeah, you can go attack all the single impactor event all you want, that scenario all you want, but you're not really addressing the scenario that's emerging from the evidence. Okay, studies of more than 40 sedimentary sequences distributed across and this is addressing the question you just asked, studies of greater than 40 sedimentary sequences distributed across North and South America, Western Europe, and Western Asia document peaks in exotic Younger Dryas boundary materials, including iron-rich spherules, silica-rich glassy spherules, melt glass, nanodiamonds, iridium, platinum, and osmium. Independent groups have confirmed much of the Younger Dryas Boundary impact evidence, but others have not or have offered alternate explanations. And we have looked at some of that. I felt it was important to at least give a cursory recognition of the critics. And I actually would like to get back because I believe that the critics raised some valid points. And it is important when you are looking at any scientific controversy that you look at all sides. Now, when I started looking at the back and forth between the proponents of an impact hypothesis and the critics of the impact hypothesis, my alignment came down on the side of the proponents, obviously, because most glaringly, the opponents of the impact hypothesis provide no coherent hypothesis for what happened. You see what I'm saying? In other words, the extinction of the megafauna, and some of them do not accept the overkill hypothesis. So right there, that's saying that the loss of the Clovis culture, the extinction of the megafauna are two different unrelated events, basically, right? Then you throw in the climate change, unrelated event. They just happen to coincide in time, but they didn't really have anything, the climate change, didn't have anything to do with the extinction? Well, yes, it did, but really how? Then the question is ignored. When we look at those graphs and we see these giant spikes, to me, it's like, well, wait a second. You can't just talk about a climate change like that and ignore what's driving or causing that climate change, right? I mean, if suddenly the temperature of the planet now plunged by 8 degrees centigrade in the next 5 years, wouldn't the prudent question be, well, what's causing that? Or we just, it's just part of the natural order. We won't even address it. We won't even think about it. It just happens. No, I don't think that if you're going to be scientific, that things just happen. There are reasons. There are causes, right? Something is driving that climate change. We have the climate change. We have the Clovis culture. We have the megafaunal extinctions. We have the massive meltdowns that have to be correlated, in my mind, with climate change. Yet, I never see the proponents of the mega floods go beyond, you had this ice dam in this big lake, and the ice dam broke away, the lake drained out. But how does that relate to the climate change? How does that relate to the melting of the whole southern sector of the Cordilleran ice sheet? It seems like maybe some of them are starting to look at that by admitting, maybe there was a lake higher up further north in British Columbia that contributed to the flooding. But you still don't see, my criticism has always been this. Here's this huge lake, more than 600 cubic miles of water, held in by glacial ice, 2,000 feet deep or more, which I consider to be an impossibility. And that was the source of the floods. But no addressing or asking the question, where the hell did that gigantic mass of water filling these entire mountain valleys of western Montana come from? Where did that come from? You're not answering the question of the ultimate origin of these mega floods by saying it came from Lake Missoula, because you've got a huge mass of water there that had to get there somehow. Now, was it precipitation? I mean, so you're saying that there was enough rainfall or snowfall that it fills the whole frickin' watershed up to almost the highest level, where the only thing feeding into it is first order streams. Now, first order stream is the littlest stream. If you look at the stream and river order of, say, the North American continent, Mississippi River is 12th order. You know what that means? That means that if you start from the smallest streams that could be measured, that have generally quasi-permanent flow, not the ones that are only being fed when it rains, but where you have maybe a spring, it's feeding a stream. It feeds into another stream. So you got first order stream, second order stream. That second order stream feeds into a third order stream. Somewhere between 4, 5, 6 orders, it's going to feed into a river. That's going to be a tributary to a bigger river. That's how you get stream orders. Generally, when you have a lake forming in a catchment basin, it's being fed by all the rivers and streams into it, right? When you look at Lake Missoula, you're basically looking at 600 plus cubic miles of water that at its final stages of accumulation is only being fed by the tiniest little streams in the whole system of stream ordering. And I'm sorry, that makes no sense. So you got to say,
Wow, that's
where
cool.
did this body of water come from? So was it rainfall? Repeatedly, yes. So was it rainfall or snowfall? Well, then you got to go, well, how much rain? Now you have to look at the physics of the thing, because as the land water is deepening, it's expanding in its area. That's going to increase the rate of evaporation, right? So there are calculations, you can do those. I won't get into that now, but
yeah, and if the inflow is steady, it slows the accumulation. It slows the rise.
Yeah. I mean, take, for example, looking at the Great Lakes, I find are good analogs, or some of the bigger lakes, Great Bear Lake, or some of the bigger lakes in Canada, or even, Flathead Lake in Western Montana, or Lake Pend Oreille, and a lot of these lakes. You can basically see that there's this equilibrium between evaporation and precipitation, right? Now, sometimes you get excessive precipitation, the lake may rise, you'll get maybe a drought period, the lake level drops, but it stays within a certain range. And it's only going to rise up to a certain point at which the evaporation is going to equal the precipitation, and it's not going to accumulate any more water. Now you look at the basin of glacial Lake Missoula, and that whole thing is filled 600 plus cubic miles of water up to the first order streams. Well, that means it had to just been raining and raining and raining and raining, in my opinion, to get that. And now at the same time, you've got an environment that could support that much precipitation, but you've got right there, contiguous with that, you have to assume that there's this huge, stable glacial lobe completely sealed off with the substrate, holding back a wall, a hydraulic head, with over 960 psi at the base, at the heel of that ice dam. How plausible is that? Well, we're going to address that in detail, that question, because I have noticed I've gotten a lot of criticism from people who have really no clue what my interpretation of these flood events is, because somehow they've got the notion and they're saying, well, Randall's theory of a single mega flood isn't supported by the evidence. Look, when you say something like that, you're simply saying you have no idea at all what I'm actually talking about, okay? So the other point is that if that lake is being fed by meltwater, well, that means to produce that copious amount of meltwater, the glacial ice has to be receding. It's going to be melting back, right? But then you've got to have this perfectly stable, long ice slope completely filling the valley of Pend Oreille down to Spokane, right? We're going to get into that. We're going to look at that in detail. And I think that once you begin to look at the glacial ice dam theory, it just doesn't hold water.
That's a tangent, Randall. I love that stuff. And yeah, we're going to spend probably many episodes on that.
Oh, yeah.
We're able to broach it there, but yeah, are we going to be able to wrap up the Wendy Woolbach paper in 5 minutes or so? Because yeah.
But we'll definitely pick up next week, because this is really interesting stuff. And then we're going to segue into looking at a bit at the nanodiamonds, because that's an important and really interesting phenomena in its own. Then we're going to get into this paper. It's entitled "A Multi-Proxy Study of Changing Environmental Conditions in a Younger Dryas Sequence in Southwestern Manitoba, Canada, and Evidence for an Extraterrestrial Impact." Extraterrestrial event, published in 2019, so it's less than a year old. But what is really significant to me about this paper is it's the first paper I've really seen that addresses the idea, the possibility of a connection between flooding, which they are documenting at this Lake Hind site in Manitoba, and the evidence for an extraterrestrial event. And I think that right there, that's an important connection that I've been advocating for at least 30 years, that I think now science is actually beginning to think, hey, extraterrestrial impact event. On the one hand, we've been looking at this. You've got other groups of scientists that have been looking at the melting events. Well, maybe it's time to start looking at these together. See,
Speaking
And
of
that is-
together, I'm going to keep pushing you to use geocosmic instead of an extraterrestrial event or a cosmic event. It's a
I like it.
geocosmic event. It's the
A
Earth,
ge-
the
yes.
space interacting with the Earth.
yes, I like it. I like it. Yes, please push me in that direction. I think that's a wonderful term.
Add that in the
Geocosmic,
lexicon.
a geocosmic event.
Yeah.
People tend to know the term, what we mean by extraterrestrial, but you know, I get people, oh, you mean aliens did it?
Well,
Yeah,
yeah,
aliens.
right. You pull away from that misnomer.
Okay, so let's conclude with this then.
All right, wrap it up.
Many Younger Dryas Boundary sites exhibit evidence of a distinct peak in biomass burning associated with the Younger Dryas Boundary impact-related proxies. We now have good solid idea of what these proxies are, right? The magnetic grains, the microspherules, the iridium, blah, 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 right? Okay. Peaks in impact-related biomass burning proxies, such as aciniform soot, which is essentially grape-like clusters of soot that form out of, or typically trees, but out of or plants, but out of really hot fires. Okay. You got aciniform soot. We'll look at that a little bit in more detail next week. Have been identified in at least four previously documented cosmic impact events. Sudbury, Molnar, Manson, and the Cretaceous Tertiary. And it might be interesting to look at each of those individually for just a minute next episode, because each one has some very interesting lessons to teach us. Furthermore, it is widely accepted that biomass burning during the late Cretaceous impact event initiated a severe climate change known as impact winter. The Cretaceous impact layer broadly contains peaks in diverse biomass burning proxies, including aciniform soot, charcoal, and carbon spherules. As evidence of a high temperature event, these biomass burning proxies are also associated with peaks in high temperature impact related proxies, including magnetic spherules, melt glass, and nanodiamonds. So that's one of the things that we learned from studying the Cretaceous Tertiary boundary event, right? You had evidence for massive biomass burning phenomena, and that was associated with, as he says here, the magnetic spherules, melt glass, and nanodiamonds. So then she goes on to say that an anomalously high peak in platinum concentrations recorded in sediments and ice has been reported at or close to the Younger Dryas onset across North America, Western Europe, Western Asia at 26 sites. Now, this resulted from the paper we discussed earlier by Pateev, whatever his name is. We should call him up and say, how do you pronounce your name, so we can get it right from now on. But anyways, at 26 sites around, as it says, North America, Western Europe, and Western Asia, inspired by this discovery of the platinum layer in the Greenland ice core. So when they went and looked, guess what they found? Platinum evidence at 26 different sites in all of these different places, including an additional 8 that are included in this paper for the first time. Pateev initially, and others initially discovered this platinum peak spanning 21 years that began precisely at the onset of Younger Dryas climate episode in the Greenland Ice Sheet Project ice core. So
Brad's
there.
wearing his hat.
So I guess we'll conclude there, because the next image is a really interesting graph, and we need to spend a few minutes on the graph. So maybe we'll pick that up in the next episode. Then, like I said, we're going to segue into nanodiamonds, and then we're going to start looking at this. Several other studies that are now extending the geographic range of the phenomenon. Right? There's a really interesting paper about discoveries in the Alps, a really interesting paper about discoveries in Venezuela, right? And an extremely interesting paper documenting recent discoveries in Antarctica. So we need to talk about all of that. Then we're going to segue into looking at other consequences, I think, of this geocosmic event, which included the mega flooding. And that's where we're going to really have some fun, because, we're planning this, assuming everything's going to go, we're planning this trip next September to introduce people to some of the most magnificent and impressive and majestic mega flood features on planet Earth up in Eastern Washington. And we're considering because the first tour got filled, we're looking at possibly doing a second tour to follow up. This will be the first of a couple of tours, because we cannot, even in a week, we can't cover but maybe half, if even that, of the mega flood landscapes. But the idea of the tour would be to take people out and teach them to read the language of catastrophe as it's imprinted into the landscape, because that's what it is. It's a cipher that has essentially been there for 12 or 13,000 years, hidden, if you will, in the landscape on such a scale that we've overlooked it. See, important insight to take away. We're looking at micro scale stuff. That's what I'm calling the fingerprints. Now the footprints, some of those footprints are pretty damn awesome. Grand Coulee is a 52-mile long giant gash in the basalt bedrock of Eastern Washington that was probably cut in a matter of a few weeks by tremendous flows of meltwater coming off of the ice sheets, 300, 400 million cubic feet per second. But the thing is, just like the comments that I've gotten repeatedly from people who live in these landscapes, interestingly, I've gotten many comments were saying, I grew up in Washington and I saw these features, but I never really knew what the story was, right? Well, that's part of what our goal here will be, is to get this story out. And we'll start with the most magnificent and impressive features, because they're the easiest to learn and decipher. But then we go on from there to begin to see maybe some of the more subtle things, because these events are imprinted all over the planet. Brad and I, and I'm not going to get into a huge rant here, but Brad and I and my brother just spent Saturday doing a recon of what's called the Little River Canyon in northeastern Alabama. Evidence of mega flood right through there. And what would have led to that mega flood? What's the evidence? Well, we're going to look into that, because I want people to understand in the southwestern deserts, there's evidence of mega floods. In the southeastern woodlands, evidence of mega floods. Up in the northeast, Pennsylvania, New York, all of that area up there, evidence of gigantic mega floods. And so I want to attempt to trigger a sort of an awakening, if you will, of people's consciousness to this story that's imprinted into the landscape all around them. But they don't have the perceptual framework, the eyes to see what has created the landscape. So that is one of the primary goals of what we're going to be doing in all of these upcoming episodes.
Learning to read the footprints.
Can't wait.
Yeah.
By the time this episode comes out, we should have the email addresses active to go along with the new website. So if people want to get in touch with those about the upcoming tours, like the ones he's starting to speak about there in the Southeast, and there'll be many more planned depending on how many we can get pulled together. But the email will be tours@randallcarlson.com. Tours@randallcarlson.com. And again, we have all these addresses going to be in the show notes and the description for the videos.
Mm-hmm. We're even going to try to get Mike Normal Guy to go out with us on our next recon.
Oh man, you got to show up, people.
Mm-hmm.
Mike's going to be there. I mean, can't ask for more than that.
What can I say?
Right.
Yeah, I'm serious. Got to meet the normal guy.
All right. Well, I guess that wraps it up for this episode.
It does.
More to come.
Always more to come. As people know, Cosmographia1618@gmail.com. Yep, Brad's got his hat on, so
yep, that means we got to go.
It does.
It's ready to go.
That's
great.
Right.
Great signal.
Perfect signal. Yeah. All right, check the show notes for all the details, people. Thank you very much. Great show, guys. Good night.
Good night.
Good night.